All right, hi everyone. We're going to be solving one more example from chapter 10. This time it is question 222. So let's read the question first. Question 222. A magnetic field B is directed outward perpendicular to the plane of a circular coil of radius 0.5 meter. The magnetic field decay exponentially according to B, so we have a formula here. I'm going to talk about that one in a moment. The coil has a resistance of 10 ohm. Calculate the EMF and current induced in the coil at time 0, time is equal to 0.05 second, and time is equal to 1 second. So first, what we see on the diagram is a circular coil with a certain radius r. We're told that the radius is 0.5 meter. There's a perpendicular magnetic field pointing outward, and this magnetic field decay with time. In other words, the magnitude is lowering, is becoming lower. We are also told that the coil has a resistance of 10 ohm, and eventually we need to find the current, so we will use Ohm's law. So the current is equal to the voltage divided by the resistance. The voltage in this case is the EMF, and the resistance is 10 ohm in this case. So we already have that formula. Now, it's not asked in the question to find the direction of the current, but since we know that the magnetic field is pointing outward, and that the field is lowering, what that means is the change in flux itself is pointing into the bore because the number of field line is becoming lower. That means we have a change in flux pointing inward. That means there will be an induced magnetic field resisting this change pointing outward. So the induced magnetic field is pointing outward. We point our thumb, curl our finger, and the current is going counterclockwise in this case. All right, so it's not asking the question, but it's always nice to have a general idea of in which direction the current is flowing. All right, so let's have a look at the formula for the EMF. The EMF is equal to the change in flux, which itself is equal to the magnetic field multiplied by the area multiplied by the cosine of the angle between the two. Now, cosine of the angle between area and magnetic field, it's cosine of 0. There's the area vector and magnetic field are pointing in the same direction. This term become 1. The area, well, it's the area of the circle. It's pi r squared. So we have pi r squared. And the magnetic field is given by this formula over here. So what happened here is we can extract the area because it's a constant. We could also extract, by the way, the 1.5. I decided to keep it there. And we want to replace the magnetic field with this formula over here. So the derivative with respect to time will only apply to the term that contain the time, basically. So it is the exponential. Like I said, we could extract the 1.5. All right, so we apply the derivative with respect to time on the exponential, and when we are dealing with an exponential, we take the constant in front of the variable and extract it in front. So what we have is a minus 5 over here. So we end up, once we compute pi r squared minus 5, 1.5 multiplied by exponential minus 5. Note, we get 5.9 multiplied by the exponential to the minus 5t. There's a minus over here. I will write it, but when we do the calculation, it's useless. This minus is a hint on the direction, and it can be confusing. It's always better to use the magnitude and figure out on the diagram in which direction it is pointing. And in this question, we're not even asked about the direction. Okay, so it does not even matter. All right, so we are asked to find the EMF and current at different time now. So we have general formula for the EMF, and we simply need to input the different time and replace it with our t over here. So t is equal to 0. Well, when that term is equal to 0, this is equal to 1, which means the EMF will be equal to 5.9. We take the EMF divided by 10. This one will be very easy. We simply divide that number by 10. We get a current of 0.59 amp. All right, we follow a similar logic for B. We replace t by 0.05, and we compute the formula for the EMF. We get 4.6 volt. Again, the current, we simply divide by 10. We get a current of 0.46 amp. Follow the similar logic, but now with a time of 1 second. We replace the time by 1 second, compute everything, and we get an EMF of 0.04 volt. And same logic, we got a current of 4 milliamp in this case, or 0.004 amp. All right, so you will see in this chapter, it's always the same step. the first part generally always involve finding the EMF, all right? And sometime you will be given the change in flux directly, so a formula for the change in flux. Sometime you will be given a component of the change. So for example, in this case, we're given the magnetic field, which itself change with time, okay? We're going to see in the next few examples, we're going to consider a constant magnetic field, but the area will be changing, all right? So that's it for question 222. Let's move on to some more example.